Integration of powers of trigonometric functions. This subsection will focus on a particular strategy for integrating expressions that are products of powers of sine and cosine. Essentially, we're looking at integrals that look something like this. Integral of sine raised to the power of m of x multiplied by cosine raised to the power of n of x with respect to x now. The key thing to understand is that how we solve these integrals, the method we use, really depends on what those exponents, m and n, actually are. Are they even numbers? Are they odd numbers? That makes a big difference. For this tutorial, we're going to concentrate on the cases where at least one of those exponents, either m or n, is an odd number. We'll see why that's important in just a moment, as it simplifies things considerably. We'll deal with the even cases later, but let's build a solid foundation with the odd power scenario first. This will set us up nicely for more complex integrations down the line. And as you'll see in later slides, these techniques have real-world applications in areas like signal processing. Okay, so let's begin with the integration of powers of trigonometric functions. As we move forward in our integration techniques, we're now going to tackle a specific type of integral. Understanding the core concept. The first point here states that the fundamental goal is to transform the integral into a form where we can apply the method of substitution. Remember substitution? It's a powerful technique we use to simplify integrals by changing the variable. We want to manipulate these trigonometric integrals so that substitution becomes possible. To achieve this transformation, we rely on the Pythagorean identity. Sine squared of x plus cosine squared of x equals 1. This is a cornerstone identity in trigonometry, and it's absolutely crucial for this integration technique. You need to have this memorized. Now, this identity allows us to swap sine squared of x for 1 minus cosine squared of x, or cosine squared of x for 1 minus sine squared of x essentially. If we see a sine squared term, we can replace it with 1 minus cosine squared, and vice versa. This is where the magic happens. It allows us to rewrite the integral in terms of just one trigonometric function. Finally, the strategy is to save one factor of the function with the odd power to serve as the differential, which we'll denote as dt, and convert the remaining even powers into the other trigonometric function. Let me break that down. If, for example, we have sine to the power of 3 times cosine squared, we'll isolate one sine term, so we'll have sine squared times sine. That single sine will become our dt after we differentiate. Then, we'll use the Pythagorean identity to rewrite the sine squared term in terms of cosine. This sets us up perfectly for the substitution we'll perform in the next steps, as we'll see on slide 3. Okay, let's move on to slide 2. As we discussed on the previous slide, we're tackling integrals involving powers of sine and cosine, specifically focusing on cases where at least one of the powers is odd. Now, this slide explains how we're going to approach these integrals. So, the key takeaway here is that we're using the Pythagorean identity to strategically rewrite the integral, preparing it for a substitution that will simplify the process. Keep this in mind as we move forward, because this is the foundation of the entire method. Step-by-step integration strategy. Okay, so let's solidify our approach to integrating these powers of sine and cosine. This slide outlines a step-by-step strategy, and it's really the key to tackling these problems efficiently. Remember from the previous slides, we've established that this method works best when at least one of the exponents on sine or cosine is odd. So the first thing we do is identify the odd power. This simply means look at your integral, something of the form sine raised to the power of m times cosine raised to the power of n, and determine whether m or n is odd. It doesn't matter which one is odd, just identify it. This is important because our strategy revolves around that odd power. Next, isolate one factor. Once you've found the odd power, we need to peel off one instance of that function. Let me give you an example. If you see sine cubed, which is sine to the power of 3, we rewrite it as sine squared times sine. We're essentially saving one sine term for later use, and that's crucial. Now, convert the even power. This is where our Pythagorean identity, sine squared x plus cosine squared x equals 1 comes into play. We use this identity to rewrite any remaining even powers of the function we didn't isolate in terms of the other function. So, if we isolated sine, we'll want to express any remaining sine squared terms using cosine, and vice versa. This is the bridge that allows us to simplify the integral. After that, apply substitution. We choose the other function, the one we didn't isolate, and substitute it with a variable, usually t. So, if we isolated sine, we'll let t equal cosine x. And remember, because we isolated that one factor of sine, the remaining isolated sine term will conveniently become part of our differential, dt. This is why isolating that odd power is so important. Finally, integrate and back substitute. Once we've made the substitution, we'll be left with a simpler integral. Usually a polynomial in terms of t, we integrate that polynomial with respect to t. And then, crucially, we replace t with its original expression, in our example, cosine x, to get our final answer. These steps might seem a bit involved at first, but with practice, they'll become second nature. We'll walk through a detailed example on the next slide to really illustrate how this all works together. And remember, the key takeaways, which we'll cover later, will help you avoid common pitfalls. Real-world application. Okay, so we've just gone through the strategy for integrating powers of sine and cosine, focusing on cases where at least one of the exponents is odd. Now, let's step back for a moment and consider why we're learning this. This slide highlights the real-world applications of these seemingly abstract integrals. It's easy to get lost in the mechanics of integration and wonder when you'd ever actually use this. The answer is, quite often in fields like physics and engineering. Specifically, let's look at signal processing and acoustics. In these areas, sound waves are frequently modeled using sine and cosine functions. Think about it, a pure tone is a sine wave. More complex sounds are combinations of these waves. Now, when engineers and physicists need to analyze these sound waves, perhaps to design better audio equipment, noise cancellation systems, or even understand how sound travels, they often need to calculate things like the average power of the wave or the energy it carries over a certain time period. And how do they do that? Very often, they use integration. Specifically, they integrate powers of these sine and cosine functions. A common calculation is finding what's called the root mean square value, or RMS value, of a signal. This essentially tells you the effective power of the wave. So, while we're focusing on the mathematical technique right now, remember that it's a tool that enables us to solve real-world problems in areas that impact our daily lives. We'll now move on to a detailed example on the next slide to solidify this technique. Detailed example. Okay, let's tackle a concrete example to solidify our understanding of integrating powers of sine and cosine. On this slide, we're going to evaluate the integral, which we're calling I, and it's defined as the integral from 0 to infinity of sine cubed of x times cosine squared of x with respect to x. Now, remember from the previous slides, the key is to handle integrals of the form integral sine to the power of m of x, cosine to the power of n of x dx by looking at whether m and n are even or odd. Step 1. Identify the odd power. In our case, the power of sine x is 3, which is odd, and the power of cosine x is 2, which is even. As we discussed, we focus on the term with the odd power. Step 2. Isolate one factor of the odd-powered function. This is crucial. We rewrite sine cubed of x as sine squared of x, multiplied by sine of x. This allows us to save 1 sine x for later use in our substitution. So, our integral now becomes the integral of sine squared of x, cosine squared of x, times sine of x, with respect to x. Step 3. Convert the even power using the identity. Now, we use the Pythagorean identity, sine squared of x plus cosine squared of x equals 1. Since we've already isolated sine of x, we want to express everything else in terms of cosine of x, so we replace sine squared of x with 1 minus cosine squared of x. This gives us the integral of 1 minus cosine squared of x times cosine squared of x times sine of x with respect to x. Step 4. Apply substitution. This is where things start to simplify. Let's set t, equal to cosine of x. This is our substitution. Now, we need to find the differential dt. Differentiating both sides of t equals cosine of x with respect to x, we get dt/dx equals negative sine of x. Rearranging this, we find that negative dt equals sine of x dx. Now we substitute both t for cosine of x and negative dt for sine of x dx into our integral. This transforms our integral into the integral of 1 minus t squared times negative dt. Simplifying, we get negative the integral of t squared minus t to the power of 4 with respect to dt. Step 5. Integrate and back substitute. Now we have a simple polynomial integral. The integral of t squared is t cubed over 3, and the integral of t to the power of 4 is t to the power of 5 over 5. So, the integral of t squared minus t to the power of 4 is t cubed over 3 minus t to the power of 5 over 5. Remember the negative sign outside the integral? It becomes negative of this result. Therefore, we have negative of t cubed over 3 minus t to the power of 5 over 5, plus the constant of integration. See, finally, we need to back substitute. We replace t with our original substitution, cosine of x. This gives us the final answer. Cosine to the power of 5 of x over 5 minus cosine to the power of 3 of x over 3 plus c. And there you have it. We've successfully integrated sine cubed of x, cosine squared of x, using the strategy we've outlined. Remember to review the key takeaways on the next slide to reinforce these concepts. Key takeaways. Okay, let's recap the key takeaways from this section on integrating powers of sine and cosine. This slide summarizes the most important things to remember as you tackle these types of problems. First, we have the odd power rule. This is absolutely crucial. It states, always isolate one factor of the function with the odd power. Now, remember from the examples we worked through, like the integral of sine cubed of x times cosine squared of x, we always separated out a single sine x or a single cosine x, depending on which one had the odd exponent. This is because that isolated factor will become part of our dt, our differential for substitution. If you don't do this first step, the substitution method simply won't work. Next, we have the target substitution. This builds directly on the odd power rule. It tells us what to substitute. If you've isolated a sine x, meaning you've factored out a single sine x from the integrand, then your substitution should be t equals cosine x. Conversely, if you've isolated a cosine x, then t should equal sine x. Think of it this way. You're setting t equal to the function that will remain after you've converted everything else using the Pythagorean identity. This is important because the derivative of t will give you the necessary differential to complete the substitution. Finally, we have identity usage. The slide emphasizes that the identity sine squared of x plus cosine squared of x equals 1 is the bridge that allows the substitution to work. This identity is the key to rewriting the integral in terms of a single trigonometric function, either all sine functions or all cosine functions, after you've isolated your odd-powered term. Without this identity, you wouldn't be able to simplify the integral enough to perform the substitution. Keep these 3 points in mind, and you'll be well equipped to handle a wide range of integrals involving powers of sine and cosine. In the next slide, we'll look at some common mistakes students make, so you can avoid them and ensure you're on the right track. Common mistakes. Okay, let's move on to the final slide, which highlights some common pitfalls students encounter when tackling these types of integration problems. It's good to be aware of these before you make them, so let's go through them carefully. First, it says substituting the wrong function. Now, remember from our earlier examples, and especially from slide 5, the key is to match your substitution to the function you've isolated. So, if you've cleverly identified an odd power, let's say of sine, and you've split off a single sine factor to use as your dt, then you must substitute t equals cosine. If you then try to substitute t equals sine, it simply won't work. Why? Because when you differentiate cosine with respect to x, you get negative sine dx. That negative sign is crucial. If you try to use sine as your substitution, you won't be able to create the differential that appears in your integral, and the substitution method will fail. Next, we have sign errors. This is a really common one. When we choose to substitute t equals cosine, we know from basic differentiation that the derivative of cosine with respect to x is negative sign. Therefore, dt, which represents the change in t, is equal to negative sign dx. It's incredibly easy to forget that negative sign when you're making your substitution. Leaving it out will lead to a completely incorrect integral, even if the rest of your work is perfect. So, always double-check that you've included the negative sign when you substitute for dt. Finally, incorrect identity application. Remember, we used the Pythagorean identity, sine squared x plus cosine squared x equals 1, to rewrite our integrals in a form suitable for substitution? Well, you need to apply that identity completely. If you're aiming for a substitution involving cosine, that means all terms involving sine, except for the single sine factor you've isolated to form, dt, must be expressed in terms of cosine. Don't leave any stray sine terms hanging around. Make sure you've fully converted everything before you proceed with the substitution. So, keep these 3 points in mind as you practice, and you'll be well on your way to mastering the integration of powers of trigonometric functions. Are there any questions about these common mistakes before we wrap up?